Welcome back to Dave Does Math from Home. This is part 2 of our video on double integrals over rectangular regions. The first video went into what I hope was enough depth and detail about what those things mean and where they come from and why they do them and what they represent, so that this video we can probably just go straight into examples and talk about examples. So let's do that. Let's just make up some weird examples of multivariable functions. Let's go with 5. No, let's go with 6. 6x squared y minus 2y cubed. Let's do dx and then dy. I want dx to go from 3 to 5, and let's make dy go from 0 to 1. This seems good. So, as per our last discussion, we ignore the first integrand and the last d, so that we're looking just at this integral with dx, the inside integral, as it were, and we calculate, we do the antiderivative with respect to x. So we treat x like it's the normal independent variable. We do the power rule, or all the derivative tricks you already know for x like normal. And we're going to treat y like it's a constant. So here it's going to function like a coefficient and just sort of come along for the ride with this x. Here we're going to treat this whole piece like it's just a constant. So the antiderivative we're going to get here should probably be this x is going to go from x squared to x cubed. The y hangs out. I'm going to divide this by 3, so there'll be 2 left, minus, this is just a constant, so 2x cubed, or sorry, 2y cubed x. This is the antiderivative. I'm evaluating at 3, from 3 to 5. Ooh, 5 cubed? Yeah, we can do 5 cubed. That's fine. The dy and the first integral symbol are just going to hang out. Nothing changes there. So I'm just going to rewrite those. Evaluating this will give me 2 times 125 is 250y minus 10y cubed. That's what happens when I evaluate this at x equals 5. This is 125 times 2. This is just the 5 times 2 for 10. And now I subtract what happens when I evaluate this at 3. So this will be 2754. 54y minus 6y cubed. When you have a weird function of both x's and y's and you're doing this, one very, very important thing to note here is that at this point, the x's are gone. There are no more x's in this integral at all. And there can't be. The goal of all of these integrals is to end up with a number. We want a volume. We don't want letters to be involved in that. We're not trying to get... Here's something I probably should mention. We're not trying to get an antiderivative with a plus c at the end. Every integral we do in Calc 3 will be a definite integral because we want a numerical result. So when you have double integrals like this of multivariable functions, anytime you finish one of those integrals, you should lose a letter. This guy started with x's and y's. Now it's just y's. After we do this integral with just y's, it's all going to fall apart, and then we're just going to have just a number. We're getting rid of a variable every time we make one of these steps. So we can do this one now. Well, we can simplify it first. 250y minus 54y is 196y. Negative 10y cubed plus 6y cubed is going to be minus 4y cubed. Negative 10, positive 6, yeah. Negative 4y cubed dy. So we can handle this. We're going to do a antiderivative with respect to y. So this will become y squared. 196 over 2 should be 98. Yeah, this is 4 less than 200, then this should be 2 less than 100. Okay, 98 minus y to the 4th, evaluated at 0 and 1. That should give me 98 minus 1 minus 0 minus 0. 97 is the final answer. So this is a double integral of weird polynomial nonsense start to finish. You integrate from the inside out, only using this first variable as an actual variable. Y is constant for this first piece. Then you plug in these numbers, you get rid of your x's, you integrate again. Let's do another example. Let's do something like the integral, the double integral. What do I want to integrate? Let's integrate x cubed sine of y plus, yeah, let's go for a cosine of y as well. Let's do y first this time. Let's integrate y and then x. I want y to go from 0 to pi, and then I want x to go from 1 to 4. No, 1 to 3. Okay, so here's another double integral. This one's dy dx. So we're going to ignore this and this. We're just going to do this inside integral first. We're integrating with respect to y. So x cubed is going to hang out. The integral of sine is negative cosine y. The integral of cosine is sine. This I'm evaluating at 1 to pi, and there's a dx and an integral from 1 to 3 on the outside that I'm not dealing with yet. I just want to evaluate this. So evaluating this at pi should give me, we'll rewrite that. Cosine of pi is negative 1, so this is going to be a positive x cubed. Sine of pi is 0. So that's the evaluation at pi. Evaluating this at 0 is going to give me positive 1. So minus negative x cubed here. Evaluating sine at 0 is still just 0. So I think this should give me 2x cubed. So the integral from 1 to 3 of 2x cubed dx. All of the y's are gone, which is exactly according to plan. We just need to integrate this 2x cubed, and that should become 2/4 x to the 4th. We're evaluating this at 1 and 3. So I'm going to call that 1/2 of 81 minus 1/2 of 1. So it's probably just 1/2 of 80, which is 40. There you go. First we integrate on y, and then we get rid of the y's, so there's nothing but x's. Then we integrate on x and get rid of the x's, and then there's nothing but a number. And that's how you know you're finished. What other kind of examples can I do here? Let's do the double integral of let's do the integral of x times the sine of xy. I need bounds here. First I need to decide the order in which I'm integrating. And in this case it's going to be really important because the order in which we choose is either going to make this thing really, really, really difficult or really easy. I think we need to integrate on y first because this is a composite function. And if we integrate on y first, we can use inside-outside business. Now let's do y first, and then let's do x after we have done y. Let's do y from 0 to 1 and x from 0 to pi over 2. I just made this up, and it might not work out like I think it will, so if this all goes catastrophically wrong, we tried. Right, so we have some sort of inside-outside other business here. Inside, not how you spell that. The inside is xy, the outside is the sine of something, and the other is x dy. Because we're ignoring this dx and we're ignoring this first integrand. So we're going to set w equal to xy, and then dw would be x dy. I'm only doing this integral with respect to y, because I want it to match here. So, we do have a perfect match here, so we can call this the integral from 0 to pi over 2 of the integral from y equals 0 to y equals 1 of, this is going to be the sine of w, this is going to be dw, and then the dx is going to hang out. The integral of sine is 0 pi over 2. Integral of sine is negative cosine. W was xy. dw is gone. I need to evaluate this at y equals 0 and y equals 1. And then I'll slap a dx on the back end. So when we evaluate this at 0 and 1, we get the integral from 0 to pi over 2 of negative cosine of x minus negative cosine of 0 dx. Cosine of 0 is 1, so this is plus 1. So this thing is the integral from 0 to pi over 2 of, I'm going to put this negative sign on the outside, so I just have the cosine x plus 1 dx. Now I can integrate this with respect to x. That's fairly straightforward, I think. Integral of cosine is sine of x. Integral of x is 1. Sorry, integral of 1 is x. Evaluated at 0 and pi over 2. So this is going to be negative, sine of pi over 2 is 1 plus pi over 2 minus negative 0 plus 0. So, yeah, this whole integral is negative 1 minus pi over 2. I'm half surprised that the whole thing didn't go catastrophically horribly wrong. And I'm glad that we got to do this problem because I think this is a pretty good example of, or not an example, I think this is a good reminder that you have to remember the old integration techniques to do these integrals. You will see stuff like this, integration by substitution. You will see this pop up sometimes. you will see integration by parts pop up sometimes. I don't think there's any like weird trig integrals like we did before, and there's probably not much going on in the way of arc trig, but there might be. So if you're looking at an integral and you're like, I have no idea what to do about this, consider some of the old integration techniques that we did in Calc 2. Substitution by parts, arc trig, weird trig identities might help you. There's a lot of options to consider there. So hopefully this is enough in the way of examples for you to get a handle on it. The homework is, I think the homework is really good about easing you into these things. So the first couple problems are really straightforward, nice, easy to get a good grasp on problems, and then they'll sort of ease you into more complex problems until eventually you're doing stuff like this. So this is going to be the it. This is going to be it, the end. I tried to say it and the end at the same time. This is going to be the it. For me, try the homework, let me know how it goes. Good luck.